Okay, guys, here is a second method of solving linear equations algebraically. Again, if you want to pause the video and write these steps, then go ahead and pause. Otherwise, we're going to get started and just take a look at a few examples. So let me just say that when you're going to use elimination, it usually is used whenever we have equations written in standard form. So we have two equations here written in standard form. So I do not have an isolated variable. So I'm going to see if elimination is going to be better than substitution. So with substitution, you want to have an isolated variable. When using elimination, what we're looking for is standard form, and we're looking for a pair of opposite variables. And what I mean by opposite variables is like negative 7a and positive 7a. So this is what we're looking for. So let's look at these two equations. We have 4x plus 8y equals negative 12 and negative 4x minus 6y equals 18. Notice that my 4x and negative 4x are opposites. So what the idea is we're going to combine these two equations. We're going to add them together so that one of the variables, either the x's or the y's, are eliminated, leaving us with one type of variable. So I'm simply going to add the second equation to my first equation. This eliminates my x's altogether, 4x minus 4x, or 4x plus negative 4x. Then we have 8y and negative 6y, that's 2y, and negative 12 plus 18, that gives us 6. Now we just simply solve for the y variable, and we have y is equal to 3. So our solution has an y coordinate of 3. Now we're just going to take this y and we're going to plug it into our either equation. We can plug the y value in here or here. I'm just going to go ahead and plug it into my first equation because I have less negatives, so less error. So I'm going to say 4x plus 8 times 3, replace y with 3, equals negative 12. We're going to solve for x. We have 4x is equal to negative 36. Divide each side by 4, and the x coordinate is negative 9. This is the point of intersection. This is the solution to this system. Remember, a system is two or more equations working together to find a solution. This would be this ordered pair, these two equations would intersect or cross in coordinate 2, where we have negative positive values. We have standard form. We're looking for a pair of opposite variables. We do not have a pair, so we are going to create a pair. We can make equivalent equations just like we make equivalent fractions. So remember, if I wanted to make an equivalent fraction, I would multiply both the numerator and denominator by the same value to get 10 over 15. 2 out of 3 and 10 out of 15 represent the same amount. So we can make an equivalent equation by multiplying the entire equation by the same value. So I could see that here we have 8y. If this term was negative 8y, that would be fantastic. And we can do that by multiplying by what we need to make it what we want. I want this to be negative 8y, so the y variables will cancel. So that means I need to multiply by a negative 2. So my new equation for the second one is going to be negative 10x minus 8y is equal to negative 48. Now I'm going to combine my equivalent equation 2 with my equation 1. I'm going to add these equations together. This gives me negative 7x. My y's are eliminated, and this gives me negative 56. I'm going to divide by negative 7, and my x coordinate is going to be a positive 8. Now I can take this x value of 8 and plug it into this equation, or even this equation. I'm just going to plug it into equation 1. So right here, I'm going to take and substitute x with 8. Three times 8 is 24, plus 8y equals negative 8. Subtract 24. I have 8y is equal to negative 32. Divide each side by 8. And my y coordinate is negative 4. So our solution for this system is 8, negative 4. This would be in quadrant 4, where we have positive, negative values. Okay, let's take a look at this example. I am looking for a pair of opposites. I do not have a pair of opposite variables. I can see that if this 15y, here I have negative 15y and negative 5y. If I created a positive 15y here, that would work. So I had to think, what am I going to do to make this a positive 15y? And that would be multiplying by negative 3. So I'm going to multiply every term to make an equivalent equation. This gives us 12x plus 15y equals negative 9. Now I'm going to combine my new equation 2 with my original equation 1. I get 15x, my y's are eliminated, and this gives me negative 30. We're going to solve for x, and my x coordinate is negative 2. Now I can take this negative 2 and I can plug it into here, or even here. I'm just going to use my original equation 2. So I have negative 4 times the x value of negative 2 minus 5y is equal to 3. Multiply negative 4 times negative 2, that's positive 8. That should be minus 5y is equal to 3. We're going to subtract 8 from both sides, and I get negative 5y is equal to negative 5. Let's divide by my coefficient of negative 5, and my y coordinate is positive 1. So our solution is going to be negative 2, 1. In this example, I do not have a pair of opposites, but there's a couple of things. I could either make this x negative 6x, or I could make one of these negative 7y's positive. I think that's what I'll do. So I'm just going to multiply this one. Again, there are so many ways you can solve these, guys. So I'm going to multiply and negate all of these terms, and my new equation 1 is going to be negative x plus 7y is equal to negative 21. Now I'm going to combine this with equation 2 with commutative property. It does not matter which way that you combine these. We're going to combine and get 5x. My y's are eliminated. That was the goal, to eliminate one of my variables. And then I get negative 35. Divide each side by 5, and the x coordinate is negative 7. I can take this negative 7 and I'm going to plug it right here. So I have negative 7 minus 7y is equal to 21. I'm going to add 7 to both sides. This gives me negative 7y is equal to 28. Divide each side by my negative 7 coefficient, and the y coordinate is going to be negative 4. Our solution, our point of intersection, the ordered pair that makes equation 1 and equation 2 true, the only point is going to be negative 7, comma, negative 4, which is in quadrant 3. So they would cross in this region here. Okay, let's take a look at this example. I think our last example was a repeat. So here we have 6x minus 2y is equal to 2, and negative 9x plus 5y equals negative 16. I do not have a pair of opposites, and I don't even have a number where I just can multiply one equation by something. So here we go. Let's think about this. I can try to make 6 and negative 9 be the same coefficient by multiplying both equations. But I think I'm going to go with the negative 2 and the 5. That will keep my numbers small. And so I'm going to make this negative 2 into a negative 10. And then I'm going to make this positive 5y into a positive 10y. So we're going to multiply both equations. I'm going to multiply this by a 5. And this gives me 30x minus 10y is equal to 10. We're going to multiply this equation by 2, and that gives me negative 18x plus 10y is equal to negative 34. Now we have a pair of opposite variables. I'm going to combine these two equations. And here we're going to get, looks like 12x. My y variables are eliminated, and I get negative 24. We are solving for the x coordinate, and my x value is going to be negative 2. I can take this negative 2 and I can plug it in here, or even my new equations, but I wouldn't do the new ones because your numbers are larger, but you can. I'm just going to take this first equation, so equation 1, and substitute x with negative 2. I get negative 12 minus 2y is equal to 2. I'm going to add 12 to both sides. I get negative 2y is equal to 14. Divide by my negative 2 coefficient. And my y coordinate is negative 7. So the point of intersection is going to be negative 2, comma, negative 7. Okay, on this exercise, I want us to know how many solutions just by looking at the slope and the y-intercept. So without graphing. So when we have different slopes, we immediately know that our two lines will cross at one place. They start at different locations and they will eventually cross. So this would be one solution. In our next example, we have different starting points, different y-intercepts, and they change at the same rate. So these would be parallel lines and never intersect. So there's no common ordered pair, so there's no solution to the system. In our third example, we have different slopes. They will intersect at one point, and they actually are perpendicular lines. Remember, perpendicular lines have opposite reciprocal slopes. And then number 4, if we simplify this slope by a factor of 4, we get 3 over 2x. So we have the same slope, we have the same y-intercept, so we're going to have infinite solutions. These lines are actually identical. Remember, the point of intersection is the solution to a system, and you can solve this graphically or algebraically by substitution or elimination. It is the ordered pair that will make both equations true. So you can always check your work. I hope this helps.